Does everybody have a syllabus? Did I print out enough? Okay.
Were there any extras? I need one.
Yeah, here.
Thank you.
Yep. And the first thing I would like you to do, this is your first assignment, send me an email. So my email address is gaio.lakin. It's probably on the syllabus somewhere, maybe not, at Normandale. .edu. Send me just an email with like the subject line with your full name in it. You don't have to put anything in the body of it, just so I get a list of emails and I can make a list. And then once I get that list together, that's where so after every lecture, I'll email everybody a PDF of the lecture, and in that email will be a link of where to go on YouTube to look at the lecture video. Okay, so that'll be, I think, especially useful if you miss class. Yep.
I've already made that list.
Oh, okay.
It's called TCE
Oh, okay.
students.mnsu.edu. So if you want to just send to that,
Okay.
Becky would also get it.
Dot MNSU.
No, TCE students at
MNSU.edu. Okay. Good. So yeah, after, in the couple hours after class, you'll get an email that has that day's lecture in it, the notes to it, and it'll have a link to YouTube where you can watch the video of the lecture. Okay, so let's go through the syllabus first. Let's see. So this class is on finite elements, and there's a couple of ways that finite element classes work that are very different from each other. One way you can do a finite elements class is to go through really carefully all of the math of how to do it so that you can write your own programs that do it. Those programs, in one semester, you can't really get enough of the way through the complicated, ways of doing finite elements that you can do very complicated problems, but it gives you more of sort of a mathematical understanding. Then the other way you can do it, and that's more of what this class is I'll give just a little bit of mathematical background, and then we'll just get used to working with a software package that does all of those things well. And so you can think of this as kind of the more applied way of doing a finite elements class, where if you have a question about stress or strain in a material later on, hopefully this class will get you to the point where you can confidently go to the software, and we're going to use Creo software, but the approach is similar in different packages, where you can go to it, come up with answers, convince yourself those answers are reasonable. So that's kind of what we're trying to get done here. There are 2 books that I would like you to get for the class. They're listed on the syllabus. The first one listed it looks like this, with a car, like a sort of a CAD drawing of a sports car on the front. Creo Parametric 2.0 by Louis Gary Lamott. It's a reference book, but it also has a pretty complete tutorial inside. And so for getting everyone comfortable with Creo, you're just going to work through a lot of this tutorial. By the way, if you, as you go on, if you're ever picking up a new software package, trying to learn it, I think it's always a good idea to look for a tutorial that'll let you work through stuff instead of just trying to figure out from a textbook or something. So the idea is this book will just kind of walk you through the steps and give you a little bit of comfort using it. And then the second book listed is the Creo Simulate tutorial, releases 1.0 and 2.0. That's by Roger Toogood. Roger Toogood does a lot of Creo reference books and stuff. And so this first one, this is the fat one, but we're not going to go through a ton of this. But this is the one that's going to get you comfortable with the, like using the modeling, you know, designing the pieces, how to create these CAD objects. And this is the one that would be useful, like for interacting with the 3D printers and stuff like that. And then the second book, Creo Simulate, is the finite element package for Creo. So this is the one where we're actually going to spend more of our time and energy figuring out how to do the calculations that we need. Please, you know, today or tomorrow, sometime soon, go to Amazon or go online, see where you can get these. We're not going to do problems from these books. So, like for example, if you found a good deal on Creo Parametric 1.0, I'd say get that. There'd be some minor differences. Sometimes it'll tell you to click a button and the button will actually be over here instead of where it says. But I don't know. Sometimes I think that helps to just sort of make you think about it anyways. So just look online, get these two books as cheap as you can. Sometime in the next couple weeks, I'm going to have you start working through those tutorials.
So you're thinking within like the next week we'll be learning or using materials out of that book?
I would say within 2 weeks. Okay. And then as far as like graded projects and things, I guess let's look at the second page. There's a table that lists out all the things that that you're going to be turning in. So I'm going to start out the semester by just talking about mathematical stuff, talking about the stress tensor, how it relates to strains. We need to do that just because you need to understand it well enough to interpret the results that you're getting out of finite elements. And so first of all, there's going to be a written exam, just like a regular in-class test on that mathematical stuff. And I'll give you a list of practice problems to work on, just like I did in my Normandale classes, and solutions to those problems, so you'll know what kind of problems to expect. And if you work through those and understand them well, you shouldn't have any trouble with the stuff on the exam. And then there are going to be two more sort of in-class exams, but instead of being like pencil and paper exams, they're going to be computer exams where, you know, like I put an object up on the screen and I'll say, make this in Creo, and then tell me what the stresses are at the center of this rectangular part or something. Okay. So, coming up in a minute is a schedule for the whole semester, so you can see like when the exams are and stuff. So those are the 3 in-class exams, and those come to a total of 35% of your grade. So not a huge chunk of your grade is on those. The bigger part of your grade has to do with the projects. The deep learning activities are related to, so those are, you'll have time to do finite element analysis of a few different structures. And those structures are going to be ones that were designed and built in the structures class. Okay. Yeah. Yep.
Let
me think about that. Yeah, you could do that. Yeah, that'll work. No, no, no. And then the last thing, so the last technical outcome is apply metacognition techniques. So there's going to be a written assignment at the end of the semester where you're going to, I don't know, I need to talk to Jake more about this, but do your, wavy gravy type stuff.
They probably know more
Yeah.
than you do.
Yeah, I'm sure that's true.
The idea for the incoming students is that you write one of these memos, and that counts for everything. So it's not one memo per class, it's just one memo. So Becky will grade that, she'll get a score, and she'll just dial that score,
Okay.
and that'll count for 5%.
Okay.
Whatever we decide to grade it.
Great.
So it's one page.
Okay, so any questions about the deliverables, the stuff that your grade is based on? Yes. So there's going to be, Jake and I talked about this a little bit. My understanding is there are going to be, so there were 3 structures things done, right?
Yep.
And so each of you is going to do sort of a summary of each of those 3 structures, things that were created. And then the 4th one is going to be like a more in-depth finite element, project related to something. I don't know what. It's either going to be one of those, a more in-depth look at one of those 3 structures, or something else.
Yeah, we were thinking kind of something more complicated than what we can build. So it's,
Yeah, like a dragon.
A car or something like that. We're not going to build it, but you still might be interested in knowing some information
Yeah.
about something which we're not going to make. So it'll be a
Yeah.
simulation and analysis of something which we don't have decision about.
Right.
So that we can't validate the solution. So the whole idea
Right.
of building things, making measurements, and then doing this analysis is to be able to validate our final
Right.
element solution. That's super important whether you're doing structure or fluids or
Right.
thermal.
Yeah, that is going to be a fun thing to actually get to see how our calculated results compare to the measured
The last
results.
thing is kind of blue sky thinking, just something really cool that we'd love to see the simulation of, but we know we're not going to be able to validate the details of it.
Yeah. Okay, and
Dial real quick.
yeah.
You seem to have loaded not the latest version of the syllabus, not the one with my
Oh.
on the screen here. But people should be looking at the paper one, not the one on the
Okay.
screen.
Yes, you're right. Thanks. Nothing changed in the schedule, I don't think. So this will be okay. But yeah, the paper copy is a newer copy. All right, here's a schedule for the class on the next page, or 2 pages later. So today is Thursday, the 15th. On the week of February 3rd and February 5th, I'm going to be out of town, so there's not going to be any class. I'll, make sure that you have stuff to work through on the tutorial while I'm gone. And I'll be able to check email if anyone has questions. And then the week after that is going to be, so on Thursday, 2/12 is going to be the written exam. So that's going to be the one on just math calculations.
Hey, Guy.
Yep.
You got an office hours?
I haven't scheduled them yet, but yeah, I'm planning to what works for you guys? I don't know what your schedule is like during the day, but if office hours work right after class, maybe we should just do that.
I mean, the majority of us are pretty much here, you know, like kind of at least like try to say 9 to 5 thing.
Right.
A time either in the morning or afternoon would work well.
Okay, so yeah, anytime. Are there other class?
Schedule that we made on the whiteboard behind the projector screen, so
Oh.
maybe after class you can.
Okay, yeah.
glance at it.
Thanks. Yeah, right. I'm totally flexible too, so I can pretty much do it whenever works.
After class would be
Tuesday
ideal.
afternoons.
Okay.
Class
Yeah.
schedule. Tuesday afternoons are no class schedule, because that's when Amanda has her out.
Mhm.
So that might be a good option for other time.
Okay. And then March 5th is going to be the first computer exam. I'm thinking that that'll be just on using Creo and not the finite elements, just making sure that you're comfortable enough building parts in Creo and assemblies and whatever. The next week is spring break. Spring break! And then I'll be out of town one more week, the week of March 31st and April 2nd. So that's going to be the same thing. I'll give you some stuff to work through, and I'll be able to be in touch with you through email, but no class. And then the week after I get back from that, on Thursday, is the second computer exam. So that's going to be the one where I'm going to say build a part, and now, tell me what the stresses are, what the strains are at this point. And then I think this would normally be like the last week of classes before finals week. The deep learning activities are due. And then the metacognition thing, I guess I'm not collecting that myself. Becky will get that to me. All right, any questions about that? Or any, so now that I notice now that we've changed to 4 different deep learning activities, maybe those should be spaced out a little bit. So yeah, I guess.
I can show you my schedule.
Okay.
When the structured ones are due, and so we can maybe look at.
Okay. Yeah, that sounds good.
I just got a question. How, I guess, what skill sets should we be expected to learn FEA? Should we be at least comfortable in modeling, or, I mean?
Like by the end of the semester?
No, just to start this, what should we be comfortable?
To start. I'm going to try to make, I think the people who've taken mechanics of materials, or deform they call it here at Normandale, that'll help,
Okay.
But I'm trying to describe things in enough detail that the people who haven't had mechanics of materials will be able to follow along. But definitely statics. You're going to need to be comfortable with statics
And
calculations.
then how about using Creo? I mean,
I'm assuming that nobody has used Creo yet. Yeah. Any other questions? Yep. I don't know. That's a good question. Hmm. Huh. Okay, so I think that about does it for now for the syllabus and the format of the course. I guess one thing, so my understanding, this is a 2-credit class, so it's reasonable for me to expect you to do 4 to 6 hours, something like that, outside of class on this. So that's sort of what I'm going to shoot for. Try to give you enough work, expect mastery of this stuff at about that level. So yeah, I guess just be prepared for about that level of work, that amount of work. Yep.
So, after the course, ideally, how familiar, how advanced will we be, in all this?
Well, I think you should be able to do, basically you'll be very comfortable with linear stress and strain and small deformations. More advanced finite element stuff has to do with like big deformations and nonlinear stress strain relationship. We're not going to get into that. You need to buy a whole separate version of Simulate to even deal with that stuff. So, but I think we'll have enough time to get pretty comfortable with the stuff that tends to be more important in engineering applications. You know, I mean, overall used more often is small deformations and linear stress strain. Any other questions? Okay.
Do we need to sign this and give it to you?
Yes, I think so. They need to sign this and give it to me?
Yes, and then you sign it and give it back.
Okay, thank you.
Here you go.
All right, I guess, yeah, let's just do this right now.
You just gotta come around and sign, or?
That would be easier, wouldn't it? That makes more sense.
You need a stamp.
You're right. Let's see.
Put a little smiley face on. Do you want us to rip off the last executive work?
I'll just come around. Don't watch this part of the video. It won't be very interesting.
Did you give yours to him? Yeah, that's mine. Okay.
How many did I get?
Yeah. You found the stapler? You found the stapler?
Stapler.
I mean, I can't imagine there's gonna be
I don't know how long the bike will last. I saw there was like a learning plan to feed like the administrative password down. You email it to that group. There should be a Dropbox for it. Did you like what control do you guys? Is it my case? Okay. There might not be one they get. For the learning plan? So we should just wait until it's due, and by the time it's due, there's no Dropbox for it.
Yeah, you can use Pro Engineer.
Just email it. That's the real goal. She's like, did you specify like I just gave like that's what I'm worried about. If I tried it for a Dropbox, that might be like by virtue of being too late to pay, you know what I mean? And can I get my pen back? No.
Okay, so let's get into the math. That's what we're all here for. That's the payoff on all this. So I'm going to just start the first couple weeks, 1 to 2 weeks, is going to be an overview on elasticity. So let me just kind of break it down into the order of topics that I'm going to cover. First, what does elasticity mean?
Stretchiness?
That's a good, so that's in the right direction, but
Linear stress strain relationship?
it doesn't have to be that, but that is a common approach in elasticity, a common simplification. But elasticity, it is sort of related to the stretchiness, really, except this is kind of an important point. It's not the stretchiness that makes it elastic because, like, for example, gum stretches, but it's not elastic because if you let go of it,
It doesn't return to its default.
that's right. That's right. Elasticity is about that. If you remove the load, it goes back to its original position. A rubber band, yeah.
My underpants.
Or underpants, right. Before the 50th wash. Underpants before the 50th wash and after the 50th wash.
Let's be honest, you can get it to about 100
Yeah. So that's what elasticity is about. It's basically because of the fact that elastic objects pop back to their original position when you remove the load, you can define a relationship between the load and the shape of the object. So there's always this defined relationship between the load and the deformation, okay? So like on the 36th wash of your underpants, if you tell me how much load you apply to your underpants, I can tell you how wide the band is, okay? That's an elastic relationship between the two. If you can't do that, you don't have pure elasticity. And there are some things that are somewhat elastic, but not totally, so you need other information. We're going to be talking totally about objects where if you're given the load, that's whether you can calculate it or not is a different story, but if you're given the load, that's enough to define a deformation. Okay. What are we talking about here? So I'm going to so elasticity is a relationship between load and deformation. Our measure of load that we're going to use the whole time is stress. And stress is in a mathematical class of objects called tensors. So I'm first going to introduce you to the idea of the stress tensor. And this stress tensor is a 3x3 matrix. And it's symmetric. And the reason it's a symmetric matrix comes from physical properties of stress, like thinking about Newton's laws. And it also gives us a way to analyze the traction on surfaces, which is you can think of as like an expression of the loads that are being applied to a face on an object, to a surface. And we're going to come up with this. So the stress tensor, go back up here to the stress tensor line. I'm going to call that the matrix sigma. The squiggle underneath says it's a matrix. And in order to calculate the traction, we're going to use this relationship that says the traction, which I suppose the traction is a vector. It's a load acting on a face is equal to the stress tensor times a unit normal to the face that you care about. Obviously, I'm going to go into more detail on all this stuff. And this will be really useful in defining boundary conditions when we go into problems. Then I'm going to talk about the meaning of the principal stress. Which kind of principle is this? Two kinds of principle, 50% chance. Nope. AL. But you really opened it up for the next person who guessed. So yeah, the AL one is always talking about like the first of something, you know? And the way you can remember that is that the school principal is your pal. So now you never get that wrong again. So principal stress has to do with the fact that this stress tensor, you know, like if you think of a force vector, say the force vector is pointing in this direction, you can represent that in any coordinate system you want, right? And it doesn't change the fact that it's pointing up at the ceiling. Stress tensors work the same way. You can represent those in different coordinate systems. And if you choose one specific coordinate system, choose the right coordinate system, you end up with the principal stresses. Then we're going to talk about the equilibrium equations, elastic equilibrium equations. These come from Newton's second law. And for those of you who've taken mechanics of materials, D-form, we never saw the full elastic equations because they're a mess. And so what we did is we broke it up into a ton of different cases. And we said, if you're dealing with a problem that has these characteristics, you can figure out the stresses using this approach. And if you have a different kind, you can do it with this approach. I'm gonna show you just the full elastic equations that if, you know, they're very hard to solve, but if you can solve them, then you have the solution without breaking it up case by case. And then I'm going to define displacement. That's a measure of deformation at a given point on a body that is given by a vector. And that vector is called u, normally. And then I'm going to talk about strain. There's a few different ways of talking about strain, but one of those ways is as a tensor. And this tensor has a relationship with the displacement vector. I'll just write it up here. So think of, so this strain tensor is also a 3x3 matrix. And you can represent the elements of the matrix as like epsilon 1, 1, epsilon 1, 2, epsilon 2, 3, you know, that gives you the location in the matrix. Well, it turns out that for the ijth element of the strain matrix, the strain element is equal to the partial of ui with respect to the jth independent variable. You don't have to analyze this too much yet. I just thought I'd write it up here. Plus the partial of uj with respect to the ith independent variable. So these independent variables, we're talking about x, y, and z because that's the space that we live in. And all this means is that displacement and strain are different things, but they have a mathematical relationship. Now, the fact that we're talking about elasticity means that our measure of load has to have some kind of functional relationship with our measure of deformation. And so what we're going to use is that the strain tensor is equal to a function of the stress tensor. This is all it takes to be elastic. And we're going to be dealing with cases, so for us, we're going to get to simplify this a little more because we're going to have a linear relationship between these two. And we're also going to have a property called isotropy, and we'll see how that simplifies the math too. I'm almost done with this list. Then number 7, I'm going to give the elastic equilibrium equations in terms of the displacement vector. And even though these elastic equilibrium equations are super complicated, we will see that we can at least use them to verify answers that we know to be true from D-form. So hopefully that'll just help you kind of wrap your head around how these equations work, what these equations mean. And then the last two, I'm going to first define strain energy. So like, the easiest way to think about that is in terms of springs. The potential energy in a spring when it's compressed or stretched is an elastic, is a strain energy, I mean. So even though nothing's moving when the spring is stretched, it has energy in it that, when you let go of it, it can apply to an object. And it's the same with other elastic solids. And then the last one, this seems like such a long list, but none of these are going to take a ton of time. We're going to formulate equilibrium as the minimum of potential energy. Strain energy is part of potential energy, so this will be using that idea of strain energy. So basically, the two final results that we're going to try to get to are, we're going to represent equilibrium of elastic objects in two different ways. One is as a differential equation, and then one is as the minimum of potential energy. That minimum of potential energy is actually the mathematical starting point of finite elements. So once we get to this, there's a lot of different ways to do that minimization, and we're not going to go into those, but I think it'll be helpful to understand how it works up to that point. Any questions about any of that, the directions we're going? So hopefully we're going to do this in 2 weeks, 1 week. Okay, so I'm going to start by talking about the stress tensor. In mechanics, one of the main goals is knowing the stress and strain at every point in an object. Okay, so an object doesn't have, I mean, in some simple cases, every point in an object can have the same stress and strain. But generally speaking, you're talking about figuring something out for just a single infinitesimal point. And you need to come up with functions that represent the changes as you go through the object. And so, so we have to understand what stress and strain are. Stress is a measure of force per area at a point. And so force per area, what are some units of force per area? Pascals, right? And I'm going to use SI units with in this class, just because that's what I'm most used to. Pascal is equal to newtons per meter squared. And then a lot of times for stresses, because the stress values are pretty big in engineering applications, megapascals is a common one, or even gigapascals. So in order to visualize the stress, imagine a cube, three-dimensional cube, with an infinitesimal size. Okay, and let's say that our x-axis goes this way, y-axis is up, and the z-axis is coming straight out of the page. Generally speaking, if this object has loads acting on it, each one of these faces will have loads on it, okay? And those loads don't have to be the same on the different faces. And so you can break down the loads in this way. Every face is going to have some kind of force-related thing, some kind of load coming perpendicular to the face. So you'll have these. And then generally speaking, they'll also have components of that load that are acting parallel to each face. So here, here, okay. And in order for this to be in equilibrium, not to rotate and not to accelerate, you need to have equal and opposite things happening on all of the parallel faces. So, for example, if this is the component in the y direction acting on the x face, like the face that, so imagine the coordinate system in the center of this cube. The x face is the one that the x-axis points to. The y face is the one that the y-axis points to. And so if you're looking at the x face, there's a component of this load acting perpendicular this way. That means that on the opposite face, there has to be an equal and opposite force going that way. Okay? And over here, if on the positive x face, you have a component of the load going up, then you have to have an equal and opposite component going down. And same with this, you have to have an equal and opposite component going this way. And that has to be true on all of these negative faces. Okay. The ones that I've drawn are called the positive faces. So can you picture why I'm calling these three the positive faces? Like again, if you think of the coordinate system as being placed right inside the cube, it's the direction those positive axes are pointing to, the face those positive axes are pointing to. Okay, so as a naming convention for these, let's take two, we're going to choose two subscripts for each one of these components. The first subscript is going to represent the face that it's acting on, and the second subscript is going to represent the direction that it's pointing in. So this one, what face is that acting on? X. And what axis is it in the direction of? X. So this is sigma xx. This one is also on the x face, but it's in the positive y direction. So this is xy. This one is on the x face in the z direction. So this is xz. And then on the y face, what's this one perpendicular to the face? YY, yep. What's this one? What direction? Q? No. X? Yeah. And then, yep, right, YZ. And then on the Z face, what's the one coming out of the Z face? ZZ, yep. So ZX, yep. And ZY. Okay, so how many total values are there that represent this stress tensor? 9 total values. And this naming convention kind of suggests putting it in a 3x3 matrix, right? So we'll represent this as a 3x3 matrix. XX, XY, XZ, YX, YY, YZ, and then ZX, ZY, ZZ. Okay, so that's 9 values. We get a break from the fact that we're always going to assume that each one of these points is in equilibrium. If you go, I'm not going to go through the derivation, but if you use Newton's second law on these 9 values, you recognize, so Newton's second law requires the following 3 relationships. Sigma xy is equal to sigma yx. Sigma xz is equal to sigma zx. And sigma yz is equal to sigma zy. So what does that tell us about this matrix? It's a symmetric matrix, yep. And that means that there are only 6 independent values. The other 3 you know from those 6. Okay, so I'm going to rewrite the stress tensor. sigma as equal to, so now we have sigma xx, sigma xy, sigma xz. This in the first time I wrote it down was sigma yx, but now because of symmetry, I'm going to leave this as